many Taiwanese students that this is probably a difficult time for you to stay on campus because that tomorrow is going to be the beginning of the long weekend. And this long weekend on Monday actually is one of the three most important holidays in Taiwan. The Mid Autumn Festival or the Moon Festival. Okay, so if you go around the stores and if you go to any of the gift shops, they probably see a lot of signs, showing you the moon. Okay, and also with the rabbits, right? I don't know whether for those of you not from Taiwan, do you understand why the rabbit? Do you know the story behind it? Okay, it was a kind of an ancient story that when you look at the moon, okay, there is a kind of you can see the shadow, and actually the shadow from the ancient old stories. Actually, there's a rabbit inside the moon. Okay, and it's kind of a lucky charm, and then there are some kind of long story about this. So, but if you look up to some of the things, and actually rabbit is cute, of course, and but also it's a sign that people because the Mid Autumn Festival actually is a feminine holiday that people would go home to celebrate holiday, and it's for people to gather together. Okay, and in some years, not until recently, there was also a tradition for people to actually have barbecue on this the Moon Festival, the Mid Autumn Festival, because that people celebrate that during the evening. Okay, and the weather is usually nice, and so usually people would go to parks, okay, or in their backyard, and they will have barbecue. They enjoy the time together. Okay, but nowadays that the government try to discourage people to go to park and to have the barbecues. Some of the reason is for the air pollution and also the environment and this and that. And so now I don't think there are so many, if you go to parks, there are so many people will have the barbecue anymore. Okay. Come on, give me a break. This is supposed to be let's see. Okay, so last time we have started to talk about the linear classifier, okay, and we have started to introduce the idea of the machine learning. And machine learning image classification is one of the tasks, okay, which we'll later talk about computer vision, but we are now using this image classification as a way of introducing machine learning, okay. So suppose that you have a picture like this, okay, and the idea here is that we have a lot of pictures, okay, and suppose that we know that some of the pictures have already been labeled previously to say that this one here is supposed to be a picture of the cat, and some of them will be the picture of a dog and the truck and planes. And can we somehow use some mechanism for machine learning to train it so that next time when it sees some picture, the picture like from picture from any of this, then you will be able to predict whatever is in that picture. Okay, and so therefore that you need to produce a label, and how good can we produce that label? What is the correctness of the label? The percentage of the label that you can predict correctly is something that we want to be able to achieve. Okay, and so basically the idea of the machine learning is to, at least in terms of the linear classifier, is to be able to to find a W. Okay, this W here has a lot of parameters, or sometimes we call weights. Okay, so if we apply some function, okay, with this W, then given any X, which is the input picture, okay, like in here, the input picture will be 32 by 32 by 3 numbers, because the 32 by 32 pixels, and each pixel actually has 3 different colors, so therefore it will be 3 different numbers. Okay, so when you have such input, the number of information, which is going to be 3,072 numbers total. When you give this as an X, okay, whether it's going to be one dimension or it's multi-dimension is, depending on how you want to structure your program. And if you use the W, which has been trained as the model, which has the parameter with the parameter, each of them with a specific weight, then you can apply certain function, okay, with these 2 parameters, and the output of the function should give you one of the classes, okay. And we can try to look at this and see how good. So, for example, here that if you have 3 different pictures, okay, and these 3 different pictures, in terms of the output, okay, which is going to be the score which they have given to predict, say, this picture here, in terms of the cat, it has a score of 3.2, and in terms of the car, it has 5.1. In terms of the frog, it's negative 1.7, okay? And we know from the label, from the original label, this one here is supposed to be a cat, okay? So we want to be able to train this W so that when we apply this F into the X and W, it should give cat the highest score, okay? And when you look at this one here, we can see the car picture, and you should see that the car actually has the highest score, okay? And so because you have many, many different pictures, and you want to be able to, all of them, should have come up with the set of the scores, and the set of score we want to always optimize, or we want to have the correct answer to have the largest score, okay? So the W here is going to be something which, depending on how many labels, how many different type of classes that you are trying to predict, okay? So here you can see that we want to produce 10. So therefore, in our input, okay, it's going to be 30, 72, 3,072 numbers, and we want to output 10. So therefore, this W here is going to be the size of 10 by 3072, because your X is going to be 3072 by 1. Okay, and so when you multiply the size of the W to be like this, then you would have, the output is going to be 10 by 1, and that is going to give us 10 different scores. Okay, so that's the idea, is that we want to be able to find the W, okay, which can produce out of these 10 scores and these 10 scores. And we have also mentioned, another idea, which is to say that there will be some, define some, let's see here, some loss function, okay? And the loss function is to say that out of the predictions that you have made, how different are they from a desirable answer, okay? And we have mentioned about 2 different possible way of defining the loss function. The first loss function here is to use a hinge loss, or the SVM, which is to say that suppose out of the pictures, okay, suppose we know that it is supposed to be, the answer is supposed to be this one, okay, the third one. Then out of the scores you have produced for them, then we will try to see that, make this one here, the 0.28 here, or this particular class, has the highest score. We want to have the highest score for this particular one. And so in here, you can see that the first one, the first class actually, is has a score of negative 2.85, and the second one is 0.86. And so this one here, we want to make this score so that the third one should be the high score and the other should be lower. Okay, so when we look at this prediction here, we will say, oh, this one here is high score. It means that the likelihood for that picture to be in this particular class is very strong. Okay, it's kind of we have a very strong kind of a reason to think that this is going to be. So the idea here is that if this is going to be 0.28, then we want to be able to say what we want to reduce the 0.86. Okay, and so that so we take this 0.286 minus 0.28. Okay, and this is going to be something we want to reduce. Okay, but if you look at this one here, this is negative 2.85, and if we take this one here minus this 0.28, already this is already a negative number. Okay, so if this is a negative number, it means that we don't really need to adjust it because it's already a low score. But if this one here 0.86 is such a high score, we want to be able to reduce this one, or we want to be able to increase the score for the third class. Okay, so we want to change our W. Okay, we want to be able to adjust the W, and so the next time when we see the same picture, okay, the score from this is going to be lower, and this one higher, and the first one is going to be lower. Okay, and then this one lower here because you can see already it's low. So when we define this particular loss function, we use this max 0 and the difference of them. Okay, even though we have a +1 here, which is to give it a bias. Okay, then you can still see that this one here actually it will be a negative value. So therefore, the max of this means that it's going to be a 0. It just means that this one here really we don't need to try to reduce it anymore. It already is pretty bad. Okay, it's a pretty low score, so we don't need to reduce it. But for this one, for the second class, okay, because right now is 0.86, so therefore 0.86 minus the 0.28 means that this one here is stronger than 0.28. Then we want to say, oh, okay, actually this value here is not good. Okay, and how bad is it? It's going to be the difference of that. And so we take the max of the 0 and this, and so that it will give us some value here to say that there is some room for improvement. Okay, so we take the max of this and max of this together, and this is going to be our total loss. It means that out of the 3 values that you predicted, okay, the total, kind of incorrect values is 1.58. Okay, so suppose we have another W. Let's just say, for example, we have another W after we have made some adjustments, and then we come up with a score. Another set of score, and suppose our next set of score, this one here is not 0.86, but this one here is 0.7, and then this one here is 0.3. If this is 0.7, this is 0.3, then what's going to be the value here? It's going to be 1.4, right? It's going to be 1.4. And 1.4, if we take the max of 0 and 1.4, then this value here is going to be 1.4. It means that we are going to have a better result because this is 0.7 only and this is 0.3. So we have adjusted our report. Now, this one here is getting lower probability, likelihood, and this one here has a high likelihood, and 1.4 means that your loss has been reduced. So our idea here is that we want to be able to use some algorithm. We gradually change this, and whenever we change this, then we can see that our correct prediction is getting stronger and stronger, and our correct prediction is getting weaker and weaker. That's the whole idea of the machine learning training. Okay, so by using this one here, eventually we want to be able to say, how do I use this loss function here to go to update the W, and so that can help us improve, okay, the prediction from all of this. Okay, so this is one way to say define the loss, which is to just take each individual score and see their difference, and then use this max value here and the SVM formulation here to say that anything which is too high of a score than my correct answer, I want to change it. I want to make it lower. But anything which is already lower than my correct prediction, then I don't need to worry about it. So therefore, it wouldn't cause any loss at all. Okay, so this is the SVM. Another way we have also mentioned is a softmax. And softmax, rather than just take the score individually, we convert each of the score by an exponential function and then normalize it so that it becomes to be, kind of a probability for each of the class to be the label. Okay, so in this case, you can see that we still want this third class to be the one which is going to be the correct answer. And so therefore, you can see that in this one here, after taking the score and using the exponential function and then using the normalized, then we have this third class here now has a score of 0.353, okay? And then the others has certain probability, like the middle one is 0.68, and this one is 0.016. Then well, our conclusion is to say that actually what I want to have, my perfect score would be for the third class to be 100% as much as possible. It means that I'm certain, okay, I want the probability for me to predict to be the third class is the highest. So right now, this is only 0.353. So we'll take the negative value of the log of this 0.5353. And so therefore, this one here will give us the value, which is going to be a positive value, which is 0.452, okay? And we will use this one here as a loss function score, okay? And then we use this one here to try to say, okay, I don't care about other probability, but for this probability right now, it's only 35%. It's 0.35. That's not good enough. I want this one here to be as high as possible. Okay, if eventually I can have this one here to be 1, and the others will be 0, of course. If this one is 1, what's going to be the loss value? If this value is 1, then you plug this 1 in here, log 1. What is log 1? 0. Okay, negative 0 is 0. It means that loss is 0. It means that when you have a perfect answer, then you would not have any loss function at all. You don't have any loss value at all. So once your loss value is 0, when you go back to try to update the W, you will say, well, your loss is already 0, so you don't need to update it anymore. Okay, so the lower this probability is, the bigger the loss value will be, and the more change we will be making to the W. And similarly in here, okay, the higher those values, not the correct answer, okay, then you can have a bigger difference, right? And whenever you have bigger difference, then your loss value will be higher. So whenever you have a higher loss value, they will make your W here to be changed, kind of more, we want to change the value here in a stronger way, and so that you will be able to improve the result. Okay, so the loss function, okay, is something that can be defined in many different ways, okay, and depending on your specific formulation, okay, and so what we have just mentioned is just for one particular class. Okay, if we know that this picture here is supposed to be third class, then we can calculate the loss to be in this way. Okay, and suppose that we have, say, for example, 100 pictures. Each pictures using the same W here would give us one specific loss value, right? Because each of the picture using the same W, then you produce a score like this way, just like what we have seen in here. When you have like this one here, you can see that this picture here will have this value, this picture will have this value, this picture. So we'll have And the total loss value for all pictures together is going to be like this. It's going to be that particular individual loss depending on your F and your YI. Okay, so this is going to be each of the I, which is each of the picture in our training data set, is going to have a loss value. And we're going to take the sum of that and do 1 over n. Sorry, that computer, or I don't know whether, I don't think it's a computer, I think it's the compatibility between the projector and the line. Okay, so the total loss for the W, okay, for the current W, given the same data set, is going to be defined by this L, which is going to be 1 over n, and then each individual pictures, will be calculated with will come up with a loss value. Okay, and so that is going to be the total loss value. Okay, and one way we can do is simply to say, okay, I'm going to use this loss value, and I'm going to try to use that to update my W. Okay, and that will be something like this. Okay, you can have the W value of the matrix. Okay, W is going to be, and this is going to be what we call as the data loss. The loss calculated purely from the training data. Okay, but quite often when we do the try to do the training, we want to use another term for our loss value. We don't just use from the loss calculated by all the training data. We want to add an extra term here, okay? And this term here there are two values. One is lambda, and the other one is R. R is the function which defines some value based on the current value of the W. Okay, so this R of W is kind of a different way for us to be looking at W. Say W is a current matrix. And so this one here is something that we're going to define, and I'm going to show you some example later. And this one here would tell us, say, how good is the W, not in terms of the loss we have just calculated, but some other properties about that W. Okay, and that R here is going to be used to evaluate. Every time when you produce a new W, we'll be evaluating that particular set of values of the W, and our W will give us some value. Okay, you can think of this R here is kind of just to review the current values of the W, okay, to see that whether it's in a reasonable shape or is it a reasonable distribution or reasonable something, okay? And simply say, well, I like the way W looks right now, okay? And I want to use this one here to say your loss is not just total depending on the data, but also depending on some property, okay? So that we will be able to say, well, because training data, after all, just the training data. Eventually, we want to use the model to be able to do the prediction on some test data set, okay? And if we try to use just the training data, then we might have the system to be too much depending on the current training data. Then, unfortunately, later on, when you have something which is not in the training data, then your system may not perform so well. So the regulation here is to say, prevent the model from doing too well on the training data. Okay, and this is a little bit of a kind of a contradictory, but I will show you. Okay, so here is an example. Suppose we have a training data set like this. Okay, we have this value, this value, this value here. Okay, so we can see that we are trying to predict between the relationship between an X and Y. And suppose now these are the training data sets we have. And after we have this training data set, we will produce a model. Probably I'll give you another X value here. And then I'll say, okay, if the X value is this, what do you think the Y value should be? Which means that where do you think the dot should be? The dot should be here, or dot should be here, or dot should be there. Okay, so if you look at this training data set, a distribution like this, as a human, what do you think should be the model? The model could be like this two different functions, F1 and F2. Okay, which one do you think is a better model for the training data set? We have 5 dots here. Is F1 good or is F2 good? If you look at how fit is a model for the training data set, definitely F1 is better, right? Because F1 is able to kind of catch every data points in the training data set. But from the human's point of view, you can see that probably you shouldn't do this. Probably F2 will be a better model. Why? Because kind of is simpler. Okay, even though F2 is not covering every node, but in terms of the trend, okay, in the trend, the model we have trend, meaning that the way that the data has been distributed, data is growing, F2 probably is better. Okay, so if I give you a new X value, if the blue line will predict the Y value to be like here. Okay, but if I use the green line, you predict, oh, the Y value should be here. Okay, so between the F1 and F2, we as a human, using our human intelligence, not the machine intelligence, we like F2 better. And so now how do we try to convince our training algorithm to say that don't use F1, use F2? And that is why we introduce this extra term here to say, well, we're going to have another way to evaluate it. So don't just trust all the training loss, data loss, but try to use something, okay, which is a measurement of how good or how likely it's going to be a more general model, okay? And what is lambda? Lambda is to say that, so we have these two possible consideration. One is purely from the data itself, and the other one is some from more, kind of different ways of looking at the model itself, okay? So between these two, which one should I put a little bit, kind of a more weight or a little bit, emphasize a little bit more, okay? And so usually we use this lambda here, which is going to be a value between 0 and 1 to say that how much of this I want to use to move the loss values to be, kind of away from the data loss. If I have a strong lambda here, and if my R here give you a bigger value, then I wouldn't be trusting the data so much anymore. Okay, but that's not what I want. I usually want to have the lambda here to be some small value so that we'll be able to say, yeah, I know that F1 can give us a very good fit, but still I'd like F2 to be, kind of a simpler model and in a way that it is more general. And so therefore I want to have some way to tell F2 to say, okay, I trust you more. Okay. And so again, between these two, definitely this one here is something we have a very good formula. We have the SVM, we have the other ways. What do you call that? That we use the normalization and this one here. Okay, so we have these two. One is a softmax. I'm sorry, one is a softmax, and the other one is SVM. Okay, so we have these two different loss function definition that can help us define this. But the R of W here is something that we're going to talk about. That it's going to be something when you're doing the training. Okay, it will just give you some extra values to evaluate. Okay. And the lambda here, as I said, that it's just simply to say that how much should I use that to affect my L, okay? And so therefore, this is called a regularization strength, okay? So the regularization term here, okay, again, we can have different ways to be defining that. And one way to define that is to use the L1 regularization. The L1 regularization simply is to say that the W here is going to have a lot of these parameters, right? So we will just try to take all parameters, absolute value, and add it together. So we'll take all of this, add it together, okay, and make this to be the total value of the R of W. What does it mean? So the R of W here is going to be something about the total values, regardless is a negative value or the positive value. Okay, we're going to take absolute value. So we want to make this one here to be, because the loss function is that we want it to be small, and so therefore this R of W means that we want to try to have the model to have smaller individual values. Smaller individual value. Why? It's kind of to say that we prefer our system, okay, to be something which is going to be every parameter here is not a huge infinity value. We prefer all of them to be smaller value because we want them to be kind of helping us to decide how we should be doing, going to be, kind of making our system to be changed. And we don't want to see the LW here totally is going to be too big a value. We want to gradually change or modify our W so that our W eventually will become the value. And if you have this, each of this W here to be a very huge value, then your weights is going to be very big, okay? And when your weight is very big, you're going to see that you're going to be moving your predictions from one end to another end and to this end to this end, okay? It's going to be doing too much of a string. But if you have a smaller value, okay, then whenever you make the extra next prediction, it probably will be making some small changes. And two ways to be measuring how big are the value. One is going to be taking the absolute value and add it together, and the other one is take the W, the square value, and add it together. Okay, and this one here is called the L2, and this one is called L1. Which one do you think would capture the idea to say that we want to have smaller W? So suppose I give you a W, okay, and the W value, will be something. Between this one and this one, which one will measure the size of the W better? It's not so intuitive, right? Because both are actually taking some absolute value. One is the absolute value, but the other one is taking the square. So actually the square value here is going to even amplify the size even more. Okay, so this the L2 regularization actually is going to make the difference of the W to be even more kind of obvious. Okay, and so there are different ways to. So if we look at this one here, okay, suppose that we have some input right now is 1111, okay, and suppose that we have two possible W, okay, and both of them you can see that when you try to to do the multiplication, all of them would give you the answer to be 1. Okay, but if you compare between this W1 and W2, think about in terms of the model. The model is going to be used to try to multiply into the inputs, right? So even though this one here and this one here multiply together, they are all 1, but W1 is actually taking a 1 here, and you will be taking just the first value of the X into consideration because the rest of them will be 0, right? And so therefore, you can imagine that you have a weight function, say that I have 4 input channels or input, individual thing, okay? But actually, when I'm trying to make my prediction, I will be using only the first one. But the W2 here actually says 0.25, 0.5, so it means that it's going to be using every input value to try to make my prediction. Okay, so in terms of the picture, okay, you can see that we have already told you that when you have a cat or when you have a car or something, will be pixels. Okay, so suppose your pixel actually you have 4 different quadrants. W1 says that I don't care whether you have 4 or something. I will look at only just one corner. But W2 here said I will look at each one of them, okay, and then add it together. Okay, which one intuitively is better? W2, right? Because W2 is looking at the whole picture rather than looking at just one corner of the picture. Okay, and if you compare this, okay, in terms of the L1 and L2, what is the value of this L1? The L1 is going to be sum of all of this absolute value. So what's going to be L1 value? It's going to be 1. 1 plus 0 plus 0, right? What about the L1 value for W2? It's also 1. It's 0.25 plus 0.1. Okay, so it's going to be 1. So L1 value-wise, they are the same. But L2 value, what is the L2 value for this one? The sum of the square values. 1 again, right? What about this? Sum of the 0.25 square is going to be 0.25 square times 4. So what is the value? Don't use your calculator. Can you imagine? 0.25 times 0.5 times 4. It's going to be 0.25 because the 0.25, the last 0.5 and times 4 is going to be 1. So therefore it's going to be 0.5. Okay, so the L2 value for this one is going to be 0.25, but the L2 value for this one is going to be 1. So you can see that the L2 value for this one here actually will be smaller. And that is something that would tell us that actually its size is smaller. Okay, using the L2 to try to measure the size of the W itself. Okay, so which one of them is better? Okay, this one here in terms of the kind of how much is covering all these inputs. Okay, W2 is better, and if you use L2, then you'll be able to see the L2 actually for the W2 is smaller, and that is better. Okay, because the loss function actually we want to have the smaller loss, right? So the smaller W actually is smaller value. Okay, so L2 regularization, like to spread out all the weights to all everything, and this is something that we would prefer. Okay, so what we have defined so far, okay, is that given a W, okay, originally we have some W value, and suppose that we have been given some training data set Xi and Yi, okay, and then we are trying to design this F. F is going to be something that when we define the model, we're going to have this F value, okay, and then we try to predict, okay, what's going to be the output of this F of XIW, okay, which will give us a score, okay, then we're going to compare the score with YI, okay, plus we're going to have some regularization which measure the W, okay, and that together, regularization loss, data loss together will be our total loss. Okay, and that is going to be our total loss. And the total loss here, or the full loss here, is going to be, for the data loss is going to be 1/n every individual data entry. Okay, data points. Okay, but the R of W is going to be looking at just the W itself. It doesn't look at data at all. So no matter you have, you have 10. Training data set, or you have 100, or you have 1,000, or you have 10,000, the R of W actually will be looking at just the W itself. So actually, it's much easier to calculate. Okay, and this one here is a little technically is incorrect because there's supposed to be a lambda in front of the RW. Okay, lambda is going to be something we're going to call that to be a hyper parameter. We can decide how much of this regularization loss we want to take into consideration in order for us to define the L. Okay, so what we have talked about so far is to define the machine learning. Okay, we have the machine learning is trying to find the F, with the X, and we have the W here. And for every W, instance of the W, we will be able to calculate the loss. Okay, and then we want to use the loss here to help us come back to modify W, so that next time when we have a new set of W, we will have lower loss. Okay, and that is what we call as the optimization kind of part of the machine training. So the optimization process, usually we use the idea which is called the gradient descent. Okay, gradient descent is, you probably have seen this picture a lot. Okay, it's basically to say that when we are searching for all this W, okay, we'll be looking for this W, okay, and W, it has so many different values in there, okay, and we want to somehow look at all the possible space of the W and try to find the W which eventually would give us the smallest loss, okay? So we can think of this W here to say it's actually is a hyperdimension space. Okay. In our example here, we have if we have two values only for the W, we have the X and Y. Okay, and so therefore that it will be two-dimensional space. But in most of the time, your W here, say for example, this W here, you can see it's going to be 10 by 3072. Okay, it's going to be a lot of values in there. Okay, and the idea here is that we can try to imagine this W here to be in some kind of hyperspace. And if we put it in a three-dimensional view, it's just like we are in some terrain, in some mountain, in some valley, in some space, okay? And what we do is to be able to, among the space in here, okay, all the points in this space here, we want to find the point or position in this picture here, which would give us the smallest loss. Okay, that would be called the optimization. We want to find the smallest loss, because when you have the smallest loss, means that your prediction is the most accurate. Okay, and so so suppose that you are a tourist, okay, or you are people who are trying to do some treasure hunting, and you say, okay, in here, I don't want to find the peak of the mountain, but I want to find the lowest point of the area. How would you go about finding it? What would be your strategy? One idea, which people often do in a three-dimensional space like this, if you can have some bottle of water and then just pour it on the ground, okay, and see where the water will flow, right? Because water is supposed to go to the lowest point, okay? And that's the idea of the gradient descent, is to say, suppose I'm in any specific location, okay? Because I want to find the lowest point. So therefore, I should follow my instinct. If I'm in here, I want to go lower, then I just try to see that from this point, compared with my next position, will my next position bring me to some altitude which is lower or higher? Okay, and I will try to keep going to the lower. Okay, and so the gradient descent is basically to say that I want to search among all this possible space that here, okay, and want to try to find out which one is the lowest position. So one way is actually just random. Okay, suppose that you don't have any strategy, so you simply say, anytime among the space positions that I can have, I just randomly choose some W value. Okay, and then I calculate the loss. Okay, after I calculate the loss, I compare the current loss with all the previous loss I have found so far. If my loss is less than the previous known the best loss, then I know that I have found a new position. So it's just like in here, okay, you are going to not follow using any strategy, but just randomly pick a position and say, okay, now let's try to measure how high I am. Okay, if I find this point here to be, a certain point, okay, and if my previous point they are higher, then I say, oh, this is the current, kind of best position. Then I bring them to another point and then measure it, okay, and then just keep going, doing this way. And this way here, of course, it's just a random search. And in some systems, the random search sometimes may give you some pretty good result if you're lucky. Okay, but of course, if you have a big space, okay, this one here, it probably would take a long, long time until you cover almost every point, then you'll find the new base point. Okay, and this is a slide from Stanford, and they have done the study, and it said, oh, about 15% of the time, you may be able to find some good position, okay? And this is probably not something not very good, okay? The other strategy, just like I said, is try to follow the slope. When you are in a certain position, okay, then because you want to go lower, then you can try to feel the ground and see that which way would give you lower, okay? From this, of course, you can see very, very well that, which path is lower, right? How many of you play golf? Do you play golf? If you watch people play golf, the most difficult thing about golfing is not so much of hitting it, how far you can hit, but what? It's putting. Putting is that when you're on the green, then you have the ball and you have a hole there, right? And you can see that they often spend a lot of time studying the surface, okay, to see this and that, and then put the ball down and then decide how should they hit. Okay, it's actually hit. It's not so much you hit it high, but simply hit the ball. The ball will be able to follow the curvature of the surface. Okay, and sometimes that if you play golf, then you would know that it's very, very difficult because it's very difficult for you to see, okay, exactly which side is higher, which side is lower, and also there are other factors. So following the slope is something, okay, you think is easy, but actually, even if you go to climb some mountain, you will know that sometimes it's not so easy, okay, because that the path you're going, you may feel that you're going up, but actually you're going down, okay. Sometimes that you may have a path initially it's going up, but eventually you will go down, okay. So how do we can have a strategy so that we'll be able to follow the slope is something is quite interesting. Okay. In any case, okay, so if we decide to use the strategy of following the slope, okay, to follow the slope, then what we need to do is that every time we have a particular f here, then we need to decide what is the current gradient. Gradient means that if I move my position from x, okay, with a little bit of a change with the, to h, then what's going to be the result difference in terms of f of x plus h minus the f of x, okay, and divided by h. So this is going to be, mathematically, we know that this is the gradient. This is what try to find the derivative and other things, okay. And so the gradient descent is to say that, okay, suppose I have my current W, for example, like in this way, and this current W here will give us a loss value like this, okay? And so now I want to know how should I change each of my W value here, okay, so that I can have a smaller loss, okay? One way to do it using the gradient descent, okay, is actually to try to update one of the values with a little bit in certain way. And once I updated that, then I can use that new W here to calculate to see that what's going to be my loss value. So in here, in this particular example, you can see that this current W, the first one is 0.34, and if I added a little bit of value, then using the formula we have just seen here to calculate the L, the loss which is going to be produced in this new W is going to be 1.25322. So compared with this one, is it doing better? Yes, because this one here is a little bit smaller than that. So it means that in terms of first, the parameter here, W1, we should try to increase it, because when you increase it, then you can see a smaller loss value. Then we can do the same thing, okay, to try to do it for the second value. I can try to do it for the third value, okay? And each of this, basically, we are kind of trying to move in that direction and see how it goes. Or mathematically, we can calculate what's going to be the gradient, which is going to be taking this loss value difference and minus the change that we have made in that particular value, okay? And this one here will give us, say, oh, this one here, the gradient of this particular parameter is negative 2.5. And the next one here, the gradient for this one here is going to be 0.6. Okay, so we can calculate each of these parameters, okay, and see how much, okay, their contribution will be to the loss value, okay? And once we have find all of them, then we can decide to say, okay, what is the best way for us to be making the changes? Okay, because once we know the gradients, okay, then you can see that each of the gradient will have a different value, and among all the gradients, then we can say we should move in that direction, because if we move in that direction, then we can have biggest change in the loss. Okay, and your system can try to follow the gradient just like you follow the path when you are searching for the right, lowest position. Okay, and this is one way for us to be kind of calculating what can be the best gradient for the loss function. Okay, once we have done that, then we will be able to say, I know which one of them, okay, I should make the biggest change, and I can go back and update the W here, so that my next version of the W would have the best loss change. Okay, that's the basic idea behind the gradient descent, is that how can we use the current W and we use the definition of the loss value, the loss function, and how we'll be able to update my W. And with the computer algorithm, we'll be able to continue to do this. Eventually, we can try to minimize my loss, and that would mean that I'm going to have a very good model. Okay, my model will be able to have a good loss function. Okay, let's take a break, and then we'll come back and look at some actual implementation of this. Kind of the idea behind the gradient descent is that, suppose that we have a W, the definition of a W, okay, and we have definition of the loss functions, and for each current W instance, or the values of the W, then we can calculate the loss, and then we also will be able to calculate to see that how are we going to be able to find which of the W entries here, or the weights, okay, will give us the most significant updates in terms of loss value, okay, by changing its W value, okay. So given us this gradient values for the W, okay, this is what we call as a DW, then we will try to use the DW here, and then we can go back and then change the W, okay? So the basic idea of the gradient descent is that we can have a loop, okay? Simply every time given us some data and give us the current weights, okay, and then we also define the loss function. Then we can evaluate the gradients, okay. We can come up with the gradient, which is going to be this particular how big a difference it's going to make to in terms of the loss value. Then we take this weight gradient, okay. Then we have another parameter, the step size, as a hyperparameter to say that how much we want to use each of this gradient here to update our current weights, okay. So the thing is that we know that, okay, each of this one here, if we update that in a certain value, then it's going to make some contribution to change the loss, okay? And each of these gradient here, you can see the values, they have the larger and smaller, and you will be making this to be kind of changed, okay? And so the algorithm here simply says that, oh, you know, we're going to take the step size. The step size here means that every time when we change the W, do we want to make a big step or we want to make a small step, okay? And this one here will be deciding how much of the weights you know, will be changed. So visually, you can think of this just like, you know, you're starting from a particular position and then you are following the slope, which is defined by the gradient, okay? And then you try to, you know, keep updating until that you find the position, okay? Now, in the calculation here, you can see that we are always using data, which is going to be the complete training data set. The complete training data set, okay, to be applied to calculate the loss for all of them, okay, in order for us to evaluate the gradient. But complete data set, depending on how much data you have, is going to be a lot, okay, which means that when you're doing this evaluate gradient here, you're going to be calculating, say, for example, if you have a 10,000 input data size, then this is going to be, you know, 10,000 times. If you have 1 million, this is going to be 1 million. And even though this is going to give you the exact, you know, gradient, okay, but in terms of the calculation, this is a little bit too much. So quite often we say, well, how about let's not try to evaluate on each one of them, but can we just use some kind of a small subset, okay, of the input value, okay, and try to calculate that, and in order for us to decide how are we going to be, you know, making changes, okay, which is to say, for example, we can have the W here, and suppose that we have 10,000 inputs, okay, the 10,000 data size that we were going to be calculating, and we have to multiply this 10,000 with each of this W here, okay, then it's going to be 10,000 times. But if we decide to say, well, okay, I know that my W here is currently you know, is going to give us some idea how I should change, but I'm going to just take, you know, out of 10,000, I'm going to take 32 of them, okay, and to calculate this according to this gradient descent function, and you can come up with the L value, okay, and the L value here will be able to use that to update my W, okay, which means that in this particular function here, okay, original definition is going to be the summation of loss from I to the N, and N is the complete data set. And then this one here, if you have N here is 10,000, then this is summation is going to be over 10,000. And this is, if this is 1 million, this is going to be over 1 million. But if we don't do that, if we take only 32 or we take 64 or take 128, then this is going to be I from 1 to 128 or I from 32 or I from 64. Okay. The question is that, okay, which one should you pick? Should you pick 32? Should you pick 64? Should you pick 128? Or you can pick 256, okay? Out of 10,000 input data you have, if you pick 256, is it going to give you enough kind of knowledge for you to be updating your W, okay? that's kind of the question about the, what we call as a stochastic gradient descent, is that you use only subset of the information, okay, and then try to update your W, okay? But if you do this over and over again, out of this 10,000, suppose every time you sample only 256 points, okay, or every, 128 points, is it going to be good enough, okay? So just like, starting from one particular position, okay, you're trying to find the lowest position, okay? If you use the complete data set, okay, then you're going to be trying to go, closer and closer to this, but you're going to be going slowly because you have a lot of data points that you want to do. When you use the stochastic gradient descent, or SGD, because you are not using the complete information, so sometimes that you may be kind of moving one way and then moving another, because you are going to be looking at a subset of the information, and moving just a little bit of, using just a little bit of information sometimes will lead you to kind of an incorrect decision. Coming back to just like when you're looking at a landscape, okay, when you have a landscape, if you don't evaluate the whole thing, if you just look at certain part of the picture, okay, and then you decide to move, then you might be moving in sections, and you quite often you may have this situation that you move swimming from one position into another, and then coming back, and this is going to be taking a long time for you to be eventually reach your final points. Okay. The other problem is using this SGD, is that sometimes that your slope actually is going to be something like this, that is not always going to be all the way down, just like when you have in the mountain. Sometimes you go down and you go up and then you go down. So sometimes when you go in this way, okay, you may find that you're getting better and better results, okay? And then if you continue to move, you're going to find that you're going to be in a worse position because your loss is going to get higher. And so from just like when you put in water into the slope, you'll find that your water is likely going to go to that lower position, and then you will move up, then you'll come back to the lower position. So it might quite often that your water will accumulate in here. But if you have enough knowledge or enough kind of water, sometimes that you will be able to go beyond this, what we call as the local minimum, and then go beyond that, little slope ahead of it, and then continue to drop. Okay, how do we use a strategy that will be able to kind of come it down this way, but not just stop in here? We'll continue to move forward to say, I know that I find that in a pretty good position here, but maybe I should continue to go. Okay, well, I should keep going. Okay, that is something that we want to be able to have the strategy that we'll be able to overcome. And to do that, one way that have discovered is to not to just use just the gradient. Okay, not just to use to say that in my current position, which way should I go that I would have a better result, but to try to use another, let me see if this somehow, okay, use another parameter or another dimension of the data, is to say that whenever I'm moving, this way, continually moving this way, I should try to look at my inertia. So when I'm coming down from there and I will drop to here, I don't always stop just here, okay? But I keep certain thing, you can think of that to be momentum, or think of that to be your current speed, okay? So if you come down this way, you would go to the lower position, but there will be some inertia, there will be still some momentum to push you, continue to push you to the next position, okay? If we use not just the slope, but also this inertia, this momentum, then we will have a better chance for us to be not trapped in local minimum. But once I reach here, because the inertia says that you should continue to go. So that when you have water flowing down this way, you reach the lowest point, but you continue to go up, okay? And then maybe you will be able to overcome this local trap and then reach to the next position. And when you reach to the up after you reach the next hill, then you will likely try to find more kind of lower position. So the momentum is the concept in the machine learning they're created to say that the gradient descent is simply using the difference between x and the delta x. Okay, just try to find that between these 2 points, what is going to be the change in terms of the loss. But the momentum is going to try to create another value which is called v, which is like a velocity. Okay. So you would model the velocity, okay, to say that that is how fast you are moving forward. So you create another value which is v, and this v here is going to be your current v plus whatever the difference you are moving forward, okay? And then so you can use this v here. Then whenever you are updating your x, you'll be updating your x using your velocity, okay? And your velocity will likely bring you to be not just your current slope, but also, one a little bit more farther away, okay? And so between your current slope and also your velocity, okay, we can again try to decide to see that how much you just use the slope, or how much of this velocity you want to consider in order for you to be finding your next position, okay? So think of this again, just like if I have certain surface, if I drop the water, okay, the water most likely definitely will flow into the, according to the slope, okay? But if I drop the water continuously, then the water will not just drop, but you will continue to move forward. So actually you would have both in terms of the difference between the heights, but also the movements. Okay, so you will be pushing everything forward. And the question is how much you want to consider this velocity to be part of the way for you to be changing your topic. Okay, and so in many of this calculation, when we are deciding how do we going to be changing the x value, we will be calculating the gradient, but also we'll be calculating the velocity. And then we will take the velocity, okay, times the rho with the gradient, okay, so that we have both of them. And the value of the rho here sometimes usually could be 0.9 or something, okay, to give a little bit of the fiction so that you are not just totally relying on the velocity, but you're also using the gradient. And then these two together will be used to be updating your position, okay? So that's the way a lot of the current machine learning algorithm is used to try to make the changes in terms of your particular your current W. Okay, there are many different algorithms that people have designed by using different combinations of the gradient and the momentum, and also they're trying to see that how loss has been changed, and then some of them they definitely can adjust between when you have rely on more on the learning the velocity. Some of them rely more on the gradient. Okay, and these are the kind of the hyperparameter for you to decide that which one should you be relying more to in order for you to have a better result. Okay, learning rate is something that we can be changing in our training in order for us to try to achieve a better result. Okay, and from the experience, usually people would start with some learning rate. Okay, and then at certain point of time after you have training data for so many points, then you would either multiply the learning rate by 0.1 to have kind of a smaller learning rate. Okay, and then you can see that every time when you reduce learning rate, then the system, the loss will be dropping more. Okay, and then when the loss is getting not changed so much, then you change the learning rate again. Okay, and when you do this over and over again, eventually, even when you change the learning rate, it doesn't change the result too much. That means that your system probably has been trained quite thoroughly. So therefore, that we don't need to make changes to the learning rate. Okay. Another way for us to be changing learning rate is simply to say, I don't really try to do this stage by stage. So this is, kind of at a certain stage you change the learning rate, at a certain stage you change the learning rate, but simply that we will just keep using smaller and smaller learning rate in our calculation, and by doing this way, we can have the system hopefully that without thinking, okay, we will be able to have best result. Okay, so pretty much when we are trying to use the idea of the machine training, machine learning, is that we have this initial W. Okay, we need to come up with the loss function, and then by using the loss function, by seeing that how we are changing the W, and we'll see that how the loss function, the loss value will change. Okay, then we'll keep updating our W. Eventually, hopefully, that we're going to be able to find the point that our loss value is the smallest. Okay, when our loss value is smallest, then we say that our model now has the best result. Okay, and given all the training data that we have, then we can try to say, oh, we can have this loss value right now, but that loss value actually right now is only for your training data set. Okay, then you need to use your test data set to see that whether your result actually is good or not. Okay, if your result, the test data set, okay, says that your result is still not good enough, what do you do? It means that you still need to go to try to train your system a little bit more, okay? And depending on your hyperparameters, your learning rate is one of the hyperparameters, or you can also try to decide different ways of using different strategy and different loss functions, and see that whether your loss function, whenever you change your loss function, that would make your training to actually get a better result or not. Okay. Okay. So what we have talked about so far is to define machine learning problem as finding W. Okay, and this W here is going to have a lot of weights, and this weights here allow us to be able to calculate what's going to be the prediction, and then we can compare between the prediction and our correct output, and then define what is going to be the loss. And then we also use this regularization to help us to define the loss, so that we don't look at just the training data set, but we also use some more objective values to be able to evaluate our loss. Okay, and then we have talked about that we can use this stochastic training data set. Okay, stochastic, SGD, stochastic gradient descent. Okay, and then we have can also include some of this learning rate here to say that we are not just using the gradient descent, but we also use the momentum to be doing the training. Okay. Earlier, I have started to talk about the neural network. Okay, a neural network actually is a way for us to be able to kind of define our way to where do I go? Okay, to define this f to be equal to w times x. Okay, let me bring out this neural network here again. Okay, so neural network is to define a set of neurons. Okay, and each neuron actually can represent to have to be your input values. Okay, and then when you have input values, then we can define the W here, which is going to be, you can define that to be the weight of the connections, okay, between the neurons. Okay, so neural network, if you look at the neural network to be this way, then it's actually quite similar to when we define the F. Okay, because F is to say, given the W, given the X, you're going to be able to compute whatever is going to be the prediction. Okay, neural network give us exactly the kind of definition by saying that, okay, if I define the neurons, I define the weight on each of the links here, then I will be able to model my output. Okay, each of this output here to be taken from the x1 times w1 x2 into the w2 and add it together, and then we can have another input here, which is a built-in, which is going to the w0. W0 doesn't have to be taken from any of the x, but you can automatically have a specific value, but it's not multiplying into any of the input. Okay, and so it's just kind of a built-in w0 here. Okay. So in this way, when we use the neural network, you can see that the neural network actually is pretty powerful that can be used to model many different functions. If you have an OR function that you want to build using a neural network, you can simply have neural network to be defining your W1 to be 1, W2 to be 1, and defining your W0 to be -1. Okay, then whenever you have x1 and x2, you can see that, okay, when the x1 is 1 or 2, 1 or 0, x2 is 1 or 0, then the output actually is going to be exactly, defined as OR function. So when you have x1 to be 0, x2 to be 0, then you take this x1, multiply the weight on the link here, then you're going to have this 0 times 1 is going to be 0, 0 times 1 is going to be 0, add it together is going to be 0, and then your the W0 is -1, so therefore your final result here is going to be -1, and when you're -1 defined by this G here, the step function, then it's going to give you the output of 0. So this is going to be the result of OR. But when you change one of them to be 1, then this one here, the G here, is going to be finding that the value to be 0, and so therefore it will map to 1. Okay, if both of them are 1, then it will be map again. Your G here will say this is going to be 1, and the output will be 1. Okay, so therefore this would allow us to define a neural network, which is just like an OR function. We can also use the neural network here to define the end by changing the weight. Okay, so again we have this 2 x1 and x2 as the input, and then we simply change the weight to be 1 and 1, okay? And then change this W0 here to be -1. Then when you have this defined in this way, and your G function is still the same, then you can see that when you x1, it's I'm sorry, if we change this, the G here to be -2, then when you have both of them to be 1, then you'll be 1. But if you change any of them to be 0, then your output will be 0. Okay, so the neural network is a way for us to be modeling similar to mathematical function, but neural network can give us kind of this architecture, allow us to be not using mathematics, but using kind of network dynamics. Okay, and we will be able to, given some input values, each input value is fed into some neuron, and then going through the network, and then defining each of these functions for the neuron, then we will be able to produce the output. Okay, and that particular output is going to be depending on whatever we want to have, okay, to be our prediction. Okay, so instead of looking at to be a mathematical model or a function, I can convert that into a neural network, and then define the neural network. We'll be able to produce the function, and which is going to be the prediction. The question for us to be using just a mathematical model when we talk about the gradient descent is for us to be updating the W, the mathematical way of changing the weight, W1, W2, and such. But when we define this to be the neural network, the weight is now going to be changed to be the length. Okay, for each of this link here, okay, what should be the value on this particular link? Okay, so the input structure is going to be each of them fed into a neuron, and the output is going to be from the last neuron. And individually, each of the way here, we can change that just like the way that we are changing our weight in this original mathematics. Okay, so using the neural network, okay, our idea here is that, okay, we're going to try to have our inputs. We can have many different kind of inputs. Each of the input, will be given to one of the input neurons, and then we can set up the network. Okay, just like we set up the W, and then if we structure the neural network in the right way, and if we give the enough, each of this W here to be the correct weight, then the value we receive from the output neuron will be the right prediction. Okay, so that's why people like to use the neural network. And using the neural network also different that we can see that we can expand the structure of the neural network. We can have not just 2 inputs, we can have 3 inputs, we can have many different inputs. Okay, so we will be able to think of the inputs are kind of similar to our sensors in the real life. Okay, each of the input will be receiving some value from something, maybe from the environment, maybe from some data source, maybe from some individual pixels in a picture. Okay, and we feed those values into the neuron, and whenever we feed the data into the neuron, then the neuron will pass the information to the next neuron. Okay, when you pass the next neuron, then you would be multiplying it into their weights. Okay, and then that would give us the result automatically, passing through each of these the neurons, and then we'll be able to find the final result. Okay, and we can increase the model to have more inputs, and then we'll have more weights. Okay, and you can see that the same model can be used to expand. We can then now try to see that how, when we talk about the gradient descent, okay, the gradient descent in the mathematical model is that we have this original W, okay, and we have this loss function, okay, and then therefore that we can use the loss function to try to help us decide how we should be changing each of the W value. The same idea can be used okay, in the neural network. Okay, so we simply need to define the way for us to say we have the output from the last neuron here. Okay, but when we have last output from neuron here, then we need to have some way to decide that how good is this. Okay, how good is the output? Okay, then when we know how good is this output here, okay, then we can use that to pass it back to each of this weight here to say that, okay, I need to change your value of your W, okay? But neural network give us this kind of different way of thinking about structuring our systems, and we can try to decide that how we want to use the sensing, how to use the input, okay, and how to link them to the output, okay, and when we have just the input, okay, and the output, okay, then we will be able to have in our original formula here is going to have 1W. So our 1W here, we multiply into the input, would give us the output, which is going to be your F, okay? And quite often, okay, in our current neural networks, we are not using just 1W, but we want to use multiple layers of the W, okay, which is in terms of neural network picture, it's just like we are adding extra layers in our neural network. So whenever we have extra layers in a neural network, it will be just like we take the original input, multiply that into W, okay, our first W, okay, then the output of that, okay, we are going to decide that which one of that will be able to produce the input for the second layer. Okay, so mathematically, it's just like you have another W2. The W2 here is going to be taking the output from the first W1, okay, and then taking that as the input and then multiply that into W2 to produce the output. So from the neural network, it's just like you have the first layer here and this first layer here with all the W here, you will be producing some output. But those output would fed into the second layer. And the second layer here, again, they will be going through another set of these links or another set of weights. Okay, and another set of weights here will be taking all of these intermediate values and then produce the final output. Okay, so it's just like you are putting an extra W2 here in order for you to produce the output. Okay, neural networks can have, in the first layer, it's going to be doing like this. It's going to be producing output and give it to the second layer. And then once you have the value from the second layer, then the second layer will send that forward in order for you to have that into the final output. Okay. So if we understand that particular idea of the layers, okay, just like you are going through multiple W here, then the idea of kind of sometimes, okay, if you imagine that in the deep neural network here, okay, each of the layer here, okay, you can decide what's going to be the weight. And also each of these neuron here can have the function to say that the values I have received at this point from all of the input from the previous layer, whether there would be enough information or enough signal for me to try to pass the information to the next neuron or not. Okay, which is like, saying that sometimes your neurons, okay, even though they have received input from previous neurons, But those previous neurons doesn't really have enough information for me to be triggered, for me to be interested. Okay, if that's the case, then I will ignore those signals. Okay, so you can have filters in the middle here to say that if the value produced from the previous input and the W1, if they doesn't give me significant value, if they are smaller than 0, then I'm going to take the value at 0. Okay, because the signal is too small. And so therefore, I'm going to be 0. And when I 0 multiply into W2 different, that means that the signal will be involved. It will be ignored. Okay, so by using this extra decision here to say that I'm not just taking W1x directly always into W2, I can have this extra decision making to say that, well, sometimes that information simply is not interesting, and so therefore it creates something what we call as a nonlinearity. Okay, nonlinearity means that I'm not taking value everything from the previous layer to the next one, but I would be stopping something, and so therefore that certain values will be continued, but certain values will be stopped. Okay, and depending on how you decide to use previous, I think we have talked about. Let me see if there's different ways for us to be deciding what are the values significant enough for me to continue. Okay, the activation functions can be one of this. Okay, it could be, for example, if your input, okay, is something which is like, between the value of -10 to 10, okay, I can have a sigmoid, meaning that my output could be something, it's not a step function, but it will be something when you are closer to 0, then you start to receive some value. But when you are in the, your input is 0, then I'm going to have 0.5. But eventually, when your value is big enough, then it's going to be, having a value of 1. Okay, and sometimes it could be a tangent function like this. And quite often we use the ReLU. ReLU, just like what I have just shown you, is that if it's below certain value, okay, if it's a negative value, then I'm going to totally ignore it. But if the value is bigger than 0, then I will pass the value along. Okay, so this allows us to be able to block certain things to say, okay, those things are not important. Those things are not interesting. And if I don't pass the value forward, then it would cause my system to be, quote unquote, more efficient, because those can be considered to be like noise or something. Okay, or sometimes we want to filter out certain things that which is not interesting in order for us to try to learn something. Okay, our human body, we have that capacity. Okay, we have that capability to say that when I hear something, okay, if it's just below certain volume, then I ignore it. But once it's go beyond certain things, then I need to be aware of that. Okay, and so sometimes that for certain information, it is better to keep them to be 0 or 1. But for certain information, that it could be that you want to convert them to be either positive or negative. If it's below certain things, then it just says, oh, this is a negative result. So therefore, I don't need to worry about the absolute value, but I just need to know that, oh, this is negative. But if it's above certain value, then this is positive. So I can convert the input, okay, from some continuous value into +1, -1, or 0 and 1, or maybe just ignore the value and pass everything else forward. Okay. There are other kind of different combinations of such activation functions. But you can think of these activation functions in terms of the neural network to be something built inside of your neural network, to say that whenever I receive some information from the previous the layers, okay, I would try to make a decision in my current neuron to say that, do I need to continue with this information? Okay, if I decided not to go, forward with that information, then simply my neuron will be not passing anything, even though that you have the next way for you to continue. But here, if you have 0, then that information will not pass forward. And this will make this calculation in the next neuron here to be with less information, or you will be able to selectively decide that how you're going to be making the decisions. Okay. So one thing that we have talked about in the previous discussion of the linear classifier, the stochastic gradient descent, is that we use the loss value. Okay, and when we use loss value, then we use that to update our W. Okay, we use that to update our W. Okay, and so using the neural network, okay, we also want to be able to say, I have seen the current result, okay, from your current weight, from the inputs. So I can also define what is how good is your current network. Okay, so from the result in this current one here, I can compare that with my training data set, because my training data set, I know that given some input, I want my output to be something. Okay, and if that output is not something as what I have desired, then I can create a loss function. And this loss function here, we can use that to try to help us to go back to update the weights in the neural network. Okay, and this is the idea of the back propagation. Okay, and the back propagation is something that especially powerful in the neural network design. It's able to let us try to find a kind of a very easy way for us to be able to say, okay, as long as I define the loss function, okay, I don't need to think about the mathematics, or I can just follow the neural network, and the neural network will be able to help us to decide that how I should be updating the changes. Okay. Let's take a break right now, and we'll come back to look at the big propagation and also other things. Okay.